Okay, so day 3 of second order circuits. How many more days do we have? It's hard to get motivated. Well, we went through the process of starting, finding the initial and final values of inductor current, capacitor voltage, and then we derived the equations for source-free RLC. So you saw how that all worked. Should have been pretty familiar to you from differential equations. And then we started working on example 2. And example 2 is a source-free series RLC circuit. You're going to have to get used to identifying these, right? It's source-free and it's series, okay? Those are the two things you're going to use to figure out what table to look at in the handout that I'm going to give you eventually, to find the right formulas for all these things. It's just like, oh my God. So we're doing example 2. Here we go. Yeah. And in this case, we're given the initial values of these guys, which makes it a little bit easier. But it's still kind of complicated. And we found the based on the RLC values that alpha is actually bigger than omega, which means it's overdamped. And so that determines the form of the solution. And that means S1 and 2 are going to equal minus alpha plus or minus the square root of alpha squared minus omega 0 squared. And that's going to equal minus 2 plus or minus the square root of 2 squared minus, what? Minus 3, not 3 squared. So that's going to equal minus 1 and minus 3. So it's minus 2 plus 1 and minus 2 minus 1. This is just and that means our solution for I of t is going to be a1 e to the s1t plus a2 e to the s2t. And so I of t is going to equal a1 e to the minus t plus a2 e to the minus 2t. So we're getting close. We've got the exponents down, and now we have to figure out what the a1 and the a2 values are, and then we'll have the total solution. And we find a1 and a2 from the initial conditions. And what are those initial conditions? Well, we're given that IL of 0 equals 0, and BC of 0 equals 5. That's what we're given in the problem, right? But we have to turn those into the things that we need for the solution. And the conditions that we need are I of 0, which is IL of 0. That's 0. Okay, check. But we also need to know what di dt is at 0 plus. But we know that, VL equals L di dt, right? No big surprise. We've been saying that over and over again. VL equals L di dt. And di dt at t equals 0 is going to equal VL of 0 over L. So what do? We redraw the circuit at t equals 0, and we know those initial values, and we can plug those in. And so we can maybe squeeze this in here at the bottom. We've got an R. We've got a inductor and a capacitor. This is R. This is IL of 0, or I of 0 flowing, I equals 0 flowing through that inductor. I equals 0 flowing through that inductor. This is VL of 0. So we're basically, this is the circuit at t equals 0 plus, right? And this is VL of 0. It's kind of hard to squeeze it all in there. I don't know if you're having any better luck than I am. That's VL of 0. Can you read that? And then this is plus or minus VC of 0, which we're given as being 5. Okay, now I want everyone to look at that and try to figure out what is VL of 0. You got to reason your way through these things, right? You're going to have this situation. You're going to redraw the circuit at t equals 0, and you're going to have to figure out what is VL of 0. We know VC of 0 equals 5. You've got to reason your way through an answer of what VL of 0 is. Conceptually, there's no formula that's going to show you this. Well, I mean, there's techniques you can use. But so you know I is 0, and you know VC of 0 equals 5. So what does VL of 0 have to be? Somebody besides Mark? Or Mark? Okay, Mark, go ahead. -5. Why? Matthew's nodding. Matthew's nodding. Go ahead. I'm just saying. Yeah, the current is 0 throughout that whole loop. So there's no voltage drop through the resistor. So the only voltage in that loop, if you do KVL, is going to be VL. And the way that's oriented with the minus attaching to the plus of the VC is going to have to be opposite of that, right? And if you're not confident with that, you can just do KVL. KVL says R times I plus VL of 0 plus 5 equals 0. So VL of 0 equals -5. But you should get good at just looking at it. You know, this is the thing that I just got a text from James, who is an NPC student. Last year he was in this class. Now he's at MIT. He has to take circuits all over again. Do you want me to read his text? He's not mad. He's actually glad he took circuits, and I'll tell you why. So I'm not in circuits, but a friend of mine is. I plan to take it in the fall or spring, but my friend told me that they move fast. Like they are finished with Thevenin and Norton after week 2. They started MOSFET transistors in week 3. We're not even going to cover those. We're halfway through the semester, and he says, I quote, "It's just second order ODE hell." And course 6, which is the electrical engineering program, doesn't believe in the exponential response formula. It's all done by inspection and intuition. He's going to save me his work, so I'll be happy to send over what they're doing. So anyway, I was pretty excited to read that. MIT. Yeah. James was so psyched to get into MIT. He was just thrilled, and he's there, he's having a great time, but they're killing him, of course. It's really hard. He has to take a lot of his classes over again. I mean, he gave me a long list of classes he has to take over again. It might be farther up in the stream here. Are you interested? I mean, it's MIT though, you know, and you know, you got to sort of realize, you know, we can't kind of teach MIT level courses here. Yeah, here it is. So MIT has not given me transfer credit for chemistry, biology, physics, differential equations, circuits, materials, and Java 1 and 2. That's like 2 years. They have given me credit for calculus and linear algebra. And he only gets, the MIT only gives transfers 3 years to graduate. So he is freaking insane trying to get out. Yeah, so. Yeah, anyway. So yeah, you got to get to the point where you can sort of intuit things, right? They're all about intuition. They want you to, you know, eventually you're going to get there, but you gotta work at it, practice, right? You can't just like blow off the homework and then, you know, get ready the night before for the test. You actually have to develop the intuition. The intuition develops over time. So you can read that circuit and say, yeah, VL is 0 plus, it must be -5 when you're looking at that. You should get good at that. And therefore, di dt at 0 plus t equals 0 equals -5 over 1, because that's what L is, which is -5 amps per second. Okay, those are the two initial conditions we need to define that solution, right? Because we know that I of t has to equal a1 e to the minus t plus a2 e to the minus 2t, right? And I of 0 has to equal, well, does equal a1 plus a2, and in this case it equals 0 because we're given that in the problem. That's our first equation to define a1 and a2. And then the other one is that di dt equals minus a1 e to the minus t minus 3, what? Oh, it's 3, not -2, sorry. Did I say it was -2 earlier? I did. Sorry, this has to be -3 here. It's a1 e to the minus t plus a2 e to the minus 3t, not -2t, because the roots are -1 and -3. -3 and -3 here. A1 e to the minus t minus 3 a2 e to the minus 3t. And therefore di dt at t equals 0 is going to equal minus a1 minus 3a2. And this has to equal -5 because that was what we derived for di dt. So that gives us two equations and two unknowns. We solve for 1 and 2, and that gives us minus a1. What? I just did that already. Well, so you can basically, I guess, what are we doing? Are we adding them together? Wait, minus a1, oh, because they're the same. So a1 equals, a2 equals minus a1. So minus a1 plus 3a1 equals, it's a pretty easy one to solve, -5. So therefore a1 equals -5/2, a2 equals +5/2. And therefore the solution is I of t equals -5/2 e to the minus 1t plus 5/2 e to the minus 3t. Okay, questions? Okay, so that's just one type of the 4 different possible types of second order circuits you might get. Matthew? Why do we have to find di dt? Yeah, it's a great question. Isaac, why do we have to find di dt? But you didn't ask. If you had asked, you wouldn't have had to answer. Now you have to answer. Yeah, but why do we have to find that? David, why do we have to find di dt? Help him out. Yeah, but why do you have to do that? You have no idea, yeah, because they told you in differential equations you had to have the equation and the derivative. Hong, why do you have to have? Yeah. Yeah, so Hong says because it's a second order circuit, you have 2 constants you got to figure out. 2 constants means you got to actually have 2 initial conditions. The first initial condition can help you define, you know, like with first order circuits, all we need is 1 initial condition because that's all we need to line up the solution, right? But with second order circuits, it's unconstrained also in terms of the slope. Depending on the values of A1 and A2, you could actually have an initial slope that's completely different with different values of A1 and A2. So you need the slope to actually figure out exactly what A1 and A2 are. Isaac. In this problem, we're given actually 2 initial conditions, but not the conditions that we need. We're given that IL is 0 and VC is 5. Those are 2 initial conditions. It's sufficient for us to figure it out, but we have to turn those into the initial value of current, which we're given, but we also have to figure out the initial slope of the current, because that's going to help us figure out what A1 and A2 are, right? Knowing what VC of 0 is doesn't help us figure out what A1 and A2 is, because that's just the current. That's just talking about the current there. That doesn't reflect the voltage of the capacitor. But we can use that information to figure out what the slope is on the current from the information given. Mason.
If we're asked for we integrate that and divide by c.
Yeah, if we're asked to find VC of t, could you integrate it and divide by c? Well, because I is flowing into the capacitor. So, sorry? No, I is flowing into the plus side of the capacitor, right? Well, if we're calling this VO as VC, right? So VC of t is going to equal V0, right, plus the integral of I dt over C, right? Yeah, you could do that, or you could take the derivative and find L times di dt is going to give you VL, and then add to it, you know, you could do some, if you can't integrate, if you suck at integration, you know, you could take the derivative and also take R times I, the derivative of I times L plus R times I, and use KVL to find VC. Yeah. And this would be the integral from 0 to whatever time you're interested in, right? You have to integrate the current from 0 to t. It's kind of like a dummy variable integration. Yeah, good question, I think. So we're finding the derivative so we can know what the slope is. What does the slope reflect? Well, you know, what's unfortunate here is that we're never actually shown what the curve actually looks like. And yet, we can plot this pretty easily in FreeMat. FreeMat? Except my computer is just really slow. I'm afraid to even load it. But the initial slope is like, so what this curve actually looks like, you know, we should have a plot for all these things. I should just, what? I actually have FreeMat. Well, this machine is very unresponsive. What you could also do is, you know, if I just bring up a browser, maybe that'll be less demanding. We can, you can plot it in Wolfram Alpha. The point is, if you change these coefficients, you're going to have a different initial slope. Jeez. Really worried about this thing. I should have rebooted the machine. Why it's crawling. I don't know. I closed down all the programs that I could think that were running, but probably all kinds of spyware and everything. Yeah. So I guess I'm not going to be able to plot this. It's just should be glad that I'm able to record the lecture. So what are the time constants? Well, these time constants are tau, as you know, 3 seconds and 1/3 of a second, right, and 1 second. So if we wanted to plot, you know, -5/2 e to the minus t plus 5/2 e to the minus 3t from 0 to 4. And it completely screwed it up. So did times t there. Actually, let's use the exp function. I think it might understand that better. Exp of minus t times exp of minus 3t and it looks like this. So so that curve is a sum of exponentials, right? One of them is going, you know, they're adding together. I don't know, you know, I mean, and they form this kind of shape here, right? And what's the initial? Well, the plot here is the initial. I mean, the initial slope here is helping us determine what these coefficients are, and they're defined in such a way that they add up to 0. So the initial value of that curve is 0. It meets our initial condition, right? But if we change these initial conditions, now I don't know, but like suppose we didn't know that they had to equal 0. Well, maybe one of them is minus 3/2, and the other one is 5/2. Well, now the initial value is not going to be 0 anymore, but also the initial slope is going to be different too, right? So if we plot, actually, let me just take a screen capture of this because maybe I'll squeeze that into the lecture. I'll do it later. This is going to be really forever. But if I change it to minus 3/2, you know, it's going to have a different value. The initial slope is no doubt different, somewhat different, you know. So we need those two coefficients to be able to pin down exactly what that curve is doing. We could also arrange these things so that the initial slope, I think, is 0. We can find a solution that will have the initial slope of 0, and I don't know what that would actually, anyway, this is a digression, but there's 2 degrees of freedom basically in the solution for a second order circuit, and you need 2 initial conditions to pin those degrees of freedom down. So now we come to the source-free parallel RLC circuit, and I kind of want to go through this pretty fast because I don't think you need to see a derivation all over again of this thing. Am I right? Do you want to really see the derivation of this thing? Or can I just give you the answers? What the form of the solution is going to be like, right? I mean, if you want to, I can do it, but you're not going to ever refer to this when you're finding the solutions, right? So the answer is the same thing. The only thing different with parallel RLC is that the definition of alpha changes from what was for the series alpha was what? R over 2L. For parallel, it's 1 over 2RC. Omega 0 is still 1 over the square root, or omega 0 squared is still 1 over LC. So this is different from series. Okay, that's important. Isaac. How does the inductor affect the current? The inductor, what does the inductor do? It stores energy, and then it gives energy back out again. And so both the capacitor and the inductor are storing energy. That's what's sort of interesting about second order circuits. You have 2 energy storage devices, and they're actually exchanging energy with each other. And so like when the current is 0, the inductor doesn't have any energy, but the capacitor may have all the energy in it. And then as it evolves, maybe the inductor current has the energy and the capacitor goes to 0. Now it doesn't have any energy, right? So they're actually exchanging energy between each other. What's the difference between a capacitor and an inductor? How they store energy. Capacitor stores it as voltage, as charge. Inductor stores it as flux in the magnetic field. Yeah. 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 So they're different energy storage devices, and they're just moving energy back and forth until it all gets dissipated through the resistor, right? Every time energy transfers from the inductor to the capacitor, it has to go through the resistor because the current's, and you're losing power, I squared times R of power as that happens. So eventually the power drains out through the resistor. If you could find a resistor, like if you could put an inductor and a capacitor in a super cool, 0 degrees Kelvin superconducting, you get like no resistance in the wires, then you would have an underdamped circuit that would just be ringing like a bell. It would just be oscillating back and forth because the energy would move from the capacitor to the inductor, then back from the inductor to the capacitor, and it wouldn't get lost through the resistor as it does that. So it would just oscillate back and forth. Is that the idea of maglev trains? Not exactly, but it's not exactly, but superconducting has a lot of interesting properties, and magnetic levitation is an interesting property. It doesn't require superconductivity, but yeah. Anyway, yeah, it's just yeah, exactly. This is sort of like, why are we doing this stuff? It's just so geeky, and but there's really cool applications of this stuff. I will, I guess I'll need to dig up some really good examples to kind of. It is really hard to get through all this stuff. And unfortunately, you're not going to find it in the book. Well, the book probably has some good examples of it, but the problems don't. They're just really grinding through stuff. But these are techniques you would use to work on systems like maglev or other things, to be able to understand how they work and design them. So that's it. Alpha and omega 0 are defined. Alpha is defined a little bit differently, but the roots are still defined the same. S1 and 2 is going to be it's still going to be minus alpha plus or minus the square root of alpha squared minus omega 0 squared. That's why it's nice to put these in the terms of alpha and omega 0, because then you have a form that doesn't really depend on the actual type of circuit that you're looking at, right? If you just define alpha a little bit differently, now you can use the same form to solve parallel RLCs. You still have the same cases where, case 1 is where alpha is greater than omega 0, and that's the underdamped case, or I'm sorry, overdamped case. And that's where your solution is v of t equals, a1 e to the s1 t plus a2 e to the s2t. Oh, I should also say we're defining the solution in terms of v now, because v is the common parameter in all those elements, right? So the solution is in terms of v. So we're gonna up here we're gonna say we're sort of finding a v of t now instead of I of t. Those are the only really two differences. Case 2 is where alpha is less than omega 0. That's the underdamped case. And in the underdamped case, it's a little more complicated, right? But this is where you remember we let omega d squared equal omega 0 squared minus alpha squared. That's where you get the complex roots. And your S1 and 2 are going to equal then, minus alpha plus or minus j omega d. And your v of t is going to equal e to the minus alpha t times a1 cosine of omega dt plus a2 sine of omega dt. That's the underdamped one, right? And then case 3 is the critically damped, when alpha equals omega 0, that's critically damped. Where S1 equals S2 equals minus alpha. And that's when the solution is that v of t equals e to the minus alpha t times a1 plus a2t. Okay, so we knocked that out pretty fast, right? People do the other ones that way too. Yeah, Alex? Should there be an S2 on case 1? Yes, there should. It says S1 there, it should say S2. Mm-hmm.
For S1 and 2, I noticed that first top of the page, but S1 common equals.
Yeah, because it's plus or minus.
So S1 plus minus.
Yeah, S1 being the plus, S2 being the minus, or vice versa. It doesn't really matter. Yeah. Okay, and so now we can look at example 3, and this should end our lecture for this week. We end on example 3. And then the switch has been open for a long time. Okay, this is more typical, where we're not given the initial conditions. We're just told you got the switch, it was open for a long time, and we're closing it at t equals 0. We got to find v of t for t greater than 0. Okay, so we're gonna have to move relatively fast here. So let's get this thing out. Let's knock this thing out. I don't want to have to finish this tomorrow. So for t greater than 0, the switch is closed. Okay, and when the switch is closed, you can observe that circuit. And what happens when you close that switch is that you're kind of disconnecting the 40-volt source there because you're shorting out that source, right? You're putting a short there. And that means you've got the circuit on the right is where all the components are in parallel. It is a parallel RLC circuit. You have to see that it's a parallel circuit to apply the right formulas. If you think it's a series circuit, you're going to use the formulas for the series circuit, which aren't going to be correct. For a parallel RLC circuit, alpha equals 1 over 2 RC. That's different than it is for series. And that's going to equal 1 over 2 times 50 times 20 microfarads, 20 times 10 to the minus 6. So that is going to equal 500. Omega 0 is 1 over the square root of LC, and that's going to equal 1 over 0.4, square root of 0.4 times 20 times 10 to the minus 6, which is going to equal 354. So our roots are, well, in this case, alpha is bigger than omega 0. So again, it's overdamped, right? The typical formula for alpha says that for S says that the roots are going to be minus 854 and minus 164. So our solution is going to be of the form V of t equals A1 e to the minus 854t plus A2 e to the minus 164t. And the A1 and the A2 are from the initial conditions. No jump, etc. And IL of 0 plus equals IL of 0 minus, and BC of 0 plus equals BC of 0 minus, and then finding the derivatives and all that stuff, right? So we slide that over a little bit. Get a little more room here, I think. So, so we got to find the initial. We got to figure out what the initial conditions are, and then turn them into the form that we can use to find the solution, right? So at t equals 0 minus. Oops, at t equals 0 minus, not at equals. At t equals 0 minus. So we start before the switch has thrown. This is how we find the initial condition. This is what they want us to be able to do. We're supposed to be able to intuit these things if we're going to MIT, right? Well, the switch is open at t less than 0, so our 40-volt source is connected to the circuit through an inductor which acts like a what? Somebody else? That was incorrect. Somebody else? A short circuit. I will train you yet. So you can put a line through this thing. The inductor at t equals 0 minus is a short, and the capacitor is a what? An open circuit. And so VC of 0 minus is just going to be the voltage across the resistor when you have all the voltage, all the current going through it. There's no current that's going to go there, right? So, right, in a steady state, capacitor is an open circuit, inductor is a short circuit. So IL of 0 minus is going to equal, oh, now this is tricky because look at the way I is defined. It's going to the left. See that? So we have to, actually we don't really need a plus there, but we can just put the IL going this way. IL 0 minus is flowing to the left there, right? But the voltage source is driving things this way, right? It's going to be going against it. So IL of 0 minus is going to equal minus 40 volts over the sum of those two resistors, right? Because it's actually just a single loop. The inductor is a short, capacitor is an open circuit, so all the current is going to be flowing through the 30 and the 50 ohm resistor. So minus 40 over 30 plus 50, that's going to equal minus 0.5 amps. And that is going to, interestingly enough, it's going to, well, no big surprise, it's going to also equal IL of 0 plus, right? And that's our initial condition that we're trying to find. So that's check, we got one of them down, right? No, actually, we need to find VC of 0 plus, right? And the derivative of the voltage, right? So that's IL of 0 plus, that's interesting. But let's now look at VC of 0 minus. That's what we're going to have to find. VC of 0 minus is going to equal it's going to equal what? This is 50. Voltage drop across 50 ohm resistor, which is a voltage divider, right? So it's going to be 40 times 50 over 30 plus 50. So that's 200 over 80. $200 over 80. So that's, I think that's 25 volts. 25 volts, and that's going to equal VC of 0 plus. So that's our first boundary condition. So we need V0. Check, but we also need dV dt at t equals 0. But we know that this equals IC of 0 over C. Mm-hmm. Is it 2.5? 200 over 80, yeah. Sounds good, 2.5. Oh yeah, it's 2,000 over 80, right? Okay, so it's 25. Okay, and why is it IC over C? Because we know IC equals C dV dt. So that's why dV dt is IC over C. So how are we going to find that initial current? Well, we got to. I'm going to keep you a little bit later. If you're late for chemistry, just tell them we're doing. At t equals 0 plus, this is really only one more slide. We've got to do this. I'm going to crank out the solution right now. This is the thing. The capacitor voltage and the inductor current are invariant, so they're the same. IL of 0 plus equals still minus 0.5 amps, and VC of 0 plus still equals 25 volts. And we have to intuit a way, can use intuition a lot today. We have to intuit a way to find the derivative of the voltage at 0. Now this thing is 25 volts. We just, it's invariant, right? And IL of 0, should be that in blue. Make it more, stand out more. And IL of 0 equals minus 0.5. Yes. Okay, and so this is IL. So we have essentially, if that's minus 0.5 amps going to the left, don't we kind of have 0.5 amps going to the right through that inductor still? Can we just get rid of that negative, right? That's a lot easier to think of, right? You got 0.5 amps going to the right through that inductor. And you also have the capacitor is at 25 volts. And if you have 25 volts, which is also across this resistor, which happens to be 50 ohms, how much of that 0.5 amps is going through the resistor? How much current is going through that resistor? If you got, yeah, you got 0.5 amps going to the right through that inductor, and that resistor, which has the capacitor across it, is got 25 volts because the capacitor is at 25 volts. How much of that 0.5 amps is going through the resistor? All of it, says Alex. Yeah, because the resistor has 25 volts across it, and it's a 50 ohm resistor, so that equals 0.5. So all of it is going through the resistor. So IC of 0 plus is equal to 0, right? KCL. And that means dV dt at t equals 0 also equals 0 because it's IC over C. So now it's the derivative that's 0. So we can, this is actually a good thing. I'll plot it in Wolfram alpha again when we get the solution, and you'll see that you can combine these things in such a way that the initial derivative is 0, not the initial value is 0, right? So here's the t of d of t. Our solution is a1 e to the minus 854t plus a2 e to the minus 164t. And our v of 0 is just going to equal a1 plus a2, which is going to equal 25. And dv dt is going to equal minus 854 a1 e to the minus 854t minus 164 a2 e to the minus 164t. So therefore, dv dt, the initial slope at t equals 0, equals minus 854 a1 minus 164 A2. And that has to equal 0. And when you solve it, you're going to find out that A1 equals minus 5.16 and A2 equals 30.16. So the total solution is V of t equals minus 5.16 e to the minus 854t plus 30.16 e to the minus 164t volts. And that is the end of the lecture, except I'm going to plot this in Wolfram alpha real fast. So you can see that the initial value is going to be 25, right? Because when E is 0, 30.16 minus 5.1 is going to be 25. So the initial voltage is correct. And we can see if the slope is really 0. Everyone done? If the slope is really 0, go back here and plot. We'll plot minus 5.16 exp of minus 854t plus 30.16 exp of minus 164t. Now, what should the range of t be? The biggest tau is 1 over 164, which is about 1 over 200. 1 over 200 is about 0.005, right? We want to go 5 of those time constants. Should be like 0.025 or something. So we go from 0 to 0.025. And there's the curve. And you can see, right, it's initially, it's got a flat spot on top there, right? It's initially flat, and then it starts diving down, right? That's the response. So that's where they both had a little bit of energy, right? The capacitor had some energy and the inductor had some energy. And it went up. But with the first one, the current was 0, right? So all the energy was in the capacitor in the first one. And that's why the curve was initially 0, and then it kind of climbed up because the energy in the capacitor started dumping through the inductor. And so we got some current that came out of it. But eventually it all went back to 0 again. Yeah. That's cool. In some ways, that's cool. We'll have to do something with this. Make a big second-order circuit to shock your brother or something. That would be a good lab, right? Except you would need a really big capacitor. Yeah.